Here is the solution to the health costs practice exam. I'm going to go through from start to finish every step as if I was taking this in a real sitting. I will start with 3 files. There's a project statement, there's a Word template, and there's an RMD template. On the real exam, they're going to give you the printed out practice. They give you the printed out project statement. In this case, I'm just going to read it on the screen here. The business problem is that Freedom Health is looking to accelerate their underwriting process by building a predictive model. Insurance underwriting is when an insurance company decides whether they want to take on a policyholder or not. They decide whether they want to write a policy or if they want to reject that policy, and if they do write the policy, what level of risk they want to assign. In the past, they've used a GLM, but their VP of Data Science believes that a GBM would offer higher predictive power. They've hired your consulting firm to conduct a comparative analysis using their historical claims data. Additionally, they want to understand what demographics indicate that a policy is likely to file large claims. The data consists of the prior year's claims, along with demographic information. Your assistant has already begun this analysis and has removed outliers, missing values, releveled factors to those with the most observations, run a hierarchical clustering, fit a single GLM, fit a GBM, including tuning the hyperparameters. There are then a list of specific tasks to go through. It would be a good idea to, at this point, read through all of these tasks just so that you have a high level idea of what's coming and where most of the points will be. I can see there are 5 points just on writing a summary of the data, and then 5 points exploring some graphs, 9 points engineering features here, so I will be careful to pay attention when I get to this task. 8 points for hierarchical clustering, 20 points for 2 GLMs, 20 points just in one question, 10 points on another question related to GLMs, 5 points looking at residual plots, and then 10 points about a GBM. Then 5 points, and 23 points on the executive summary. Here's the data dictionary. There are only 1, 2, 3, 4, 5, 6, 7 variables. And so this looks like it will be straightforward. There will not be a lot of time spent on the data manipulation and so forth. So let's get started on the specific tasks. On task 1, explore the target variable charges and its relationship to smoker and BMI. So to start, I'm going to run this template code, and this will convert the factors to those with it will convert the base levels of the factors to those which have the most observations using this factor and frequency. Let's look at a glimpse. Okay, and task 1, I can say the data consists of 1338 observations of seven variables. Well, there are 6 predictor variables, which are related to the person's related to health care costs or medical claims. The target is the annual medical costs for a policy. Let's look at the histogram of target variable. We can see that it's right skewed, it's positive. I'm going to copy this as an image, and then when I paste, I go to paste special as independent bitmap. The target distribution is positive and right skewed. And the mean is 13,270, and the median is only 9,382. Task 2. Explore the target variable charges and its relationship to smoker and BMI. Perhaps this would be better off put into task 2. Let's look at the distribution now using the fill as the smoker status. You can see that the smokers uh, smokers have higher claims on average than non-smokers. The distribution of smokers is bimodal. See how there are two lumps of people right here at about 200,000 or about 40,000, about 20,000 and 40,000. I wonder why. I wonder if this is related to another variable in the data. Like we have age, sex, BMI. Maybe it's related to sex. If we do this. No, it doesn't look like this is the separating variable. That's okay. I'm just going to keep moving. Here's another way of showing this. On the left is non-smokers, on the right is smokers. Here's a graph of the charges against BMI. You can see that as charges increase, BMI tends to increase as well, which means that, so BMI is body mass index. BMI is the body mass index, which is the weight divided by the height of a person. We see that as BMI increases, the annual claims tend to increase as well. And if you add a split by smoker status, you can also see that smokers have a very different pattern than non-smokers. So smokers have for smokers, BMI has a strong correlation with charges. For non-smokers, this correlation is much weaker. Now, correlation just means how close together the points are. It measures how well the points fall into a line. You can see that there's um, almost a straight line that you could draw along these points along these people here who are smokers, whereas non-smokers are more randomly scattered. Task, let's go back to this data dictionary, to this project statement. Okay, so task 1 was write a high-level summary, include the number of records and number of variables. This is done. Task 2 is explore the target variable and its relationship to smoker and BMI. We've done that. Task 3, engineer additional features in order to improve the predictive power of the models. So we need to create some new variables. So I need to create a new copy of the data and then mutate. I need to create age bucket, which is going to be a case statement. Case when age is less than 24, then it's going to go to 1. Age less than or equal to 36, then it will go to 2. Age less than or equal to 50, then it will go to 3. And age greater than 50 will go to 4. And then I just want to look at summary. Okay, and I'll then convert this to a factor in frequency. I just say as character and then factor in frequency. Okay, and now you can see the number of records in each age bucket. Okay, so this is age bucket. The next variable is the age household ratio, which is 1 plus the number of children over age. And then log household size is equal to the log of 1 plus children. And then remove the original variables, the original children variable. And then I want to see a summary just to make sure that these values are all reasonable and that there are no missing values or NAs or NANs. And it looks like these are all okay. So I will go ahead and save this as the health insurance data. Task 4, examine hierarchical clustering of age and BMI. Your assistant has set up code to run hierarchical clustering using the Euclidean distance metric on age and BMI. Only the first 50 records are used in order to make the graphs easier to read. Rescale both variables prior to clustering and then select a cutoff height. Explain why scaling is necessary and what the cutoff threshold controls. You do not need to add the cluster column to the data or use it in the next tasks. Here you can see the code is creating a variable called age, which is taking the first 50 records. And it's also doing this for BMI. And then it says your code here, apply scaling. No code is provided. Then it puts age and BMI into a matrix, performs hierarchical clustering, plots the dendrogram. So what is scaling? What does scaling refer to? Well, before even doing anything, I'll just start by writing down what I know. First, let's fill in here. I created 3 new features: age bucket, age household ratio, and log household size. This will help to improve the predictive power of the model. Here's a summary of the values. And let's put, okay. Okay, now task 4. So I want to first write down what I know. Clustering is an unsupervised learning method that seeks to group together observations into clusters which share similar characteristics. Hierarchical clustering, I can never spell hierarchical. Hierarchical clustering starts with each observation in its own cluster and then groups together those that are similar. Then it iteratively groups these subgroups together to together in a sequential manner. And this says to use Euclidean distance, right? So what does this mean? It means that if you um, if you look at a plot between these two variables, it will try to put people into clusters based on the Euclidean distance. So this point right here, this is at about BMI equals 40, age equals 40. So point 1 is 40, 40. And then let's see this point right here. This is about 40. Well, let's look at this point over here. So BMI is equal to about 50. Age is equal to about 60. So BMI is equal to 50. Age is equal to about 60. Right? So let's call X naught is equal to 40. Y naught is equal to 40. X1 is equal to 50. Y1 is equal to 60. Now let's say this x1 is actually 60. Y1 is about 50. And how do you get the distance between these 2 points? You take the square root of the sum of, like, you take square root of 40 minus 60 squared plus 60 plus 40 minus 50 squared, right? That's Euclidean distance. And because these variables are not on the same scale, BMI goes from 20 to like 50, whereas age goes from 20 to like 60. They're not on the same scale. So if you just tried to calculate their distance directly without doing any types of rescaling, see here, age goes from 18 to 64, BMI goes from, well, but 16 to 53. So they're actually quite close, but they're not exactly identical. So what you should do is you should rescale the variables, and to do that, you can say that age is equal to age minus mean of age over the standard deviation of age, and BMI is equal to BMI minus mean BMI over the standard deviation of BMI. And then if you look at the summary of age and the summary of BMI, I can see that they both have a mean of 0, which means that they're on the same scale, which is what we want. This means that the distance is, when we try to draw the clusters here, it means that the same weighting will be given to age as given to BMI. So the distance will be comparable. I noticed Euclidean distance means that the units of age and BMI need to be on the same scale prior to clustering. Otherwise, the more weight will be given to what was it? It was age, because it has larger values. I did this. I rescaled by subtracting the mean and dividing by the standard deviation. All right. And then I can run this clustering. So this is called a dendrogram, which is just a fancy word for a way of showing the different clusters. So on the height here, you see the a way of showing the complexity, right? If you only have one cluster, then everyone would be in the same group, right? If you have two clusters right here, then all of these records would be in one cluster, and all of these records would be in another cluster. So that if you said height is equal to 2, you'll get 2 clusters. If you say height is equal to 1.5, you get 1, 2, 3, 4 clusters, and so forth. So what is this question asking? Rescale both variables, which we have done. explain why scaling is necessary, and explain what the cutoff threshold controls. So the cutoff controls how many clusters are chosen. When for the height equal to 2, there would be 2 clusters. For the height equal to 1.5, there would be 3. Okay. Each of the final endpoints on the bottom of this graph represent the case when there are 50 clusters, right? Because we have 50 data points. So if you were to count 1, 2, 3, 4, 5, 6, 7, 8, etc., you'd get 1 cluster for each observation. Okay. Task 5, fit 2 GLMs. A GLM consists of 2 assumptions. A random component, which is the response family of claims. B, a link function, the way that the mean of the claims distribution, mu, is related to the linear predictor, which is the matrix X times beta. Choose the best link function and response family combinations, 2 different models, using all variables. Base your decision off of MAE on the test set. So first I can run this code here, which will create a graph that shows the clusters by the points in the graph. So I should select a height here. So let's just say I want 1, 2, 3, 4. Let's just say I want to set this cutoff at 1. I'll set the height at 1, and then this will create like 5 or 10 clusters. Creates 9 clusters. I chose to set the cutoff at 1, which resulted in 9 clusters. Okay, now moving on to task 5. Here's some code that will create a train and test partition. I'll just run that. I'll see that 80% of the observations are in training. So first, I split the data into training 80%, testing 20%. I will train. Okay, now you can see your assistant has provided you with these functions. No changes need to be made. So there's an MAE function, which gets the MAE. There's this fit GLM function. It takes in 2 arguments. Actually, only 1 argument. It takes in a family link argument. Okay. So, for example, fit a GLM with a Gaussian response and a log link. If I run this, it will fit a GLM with a Gaussian response and a log link, and then it will get the MAE based on the test set. And it says the MAE is 4109, right? I train the model on the training data and then evaluate it on the test data. And what type of model are we using? A GLM is a way of relating the target variable to multiple input variables at once. There are two key, I'll just say the GLM assumes that the target distribution follows a specific family and that the mean of this distribution is related to the data through a link function. So it says there are many different possible families. To find possible families, use question mark family. If I run this, I will see there's binomial with logit link, Gaussian with identity link, gamma with inverse, and so forth. But I think at this point, I'm getting a little bit ahead of myself because this just says choose the best link functions and response family combinations. Base your decision off of MAE on the test set. So all that I need to do is just test out a bunch of different combinations and then choose the one that has the lowest, choose the two which have the lowest MAE. So the response, though, claims is continuous. And so we can rule out the binomial or Poisson distributions, right? So we have to test Gaussian gamma, inverse gamma, and I'm also not going to test the quasi distributions. Okay, so let's just do that. Let's test Gaussian with an identity, Gaussian with a square root. There's the Gaussian with a log. Gaussian with an inverse squared link function. And Gaussian with an inverse link. And here you can see all of the error metrics. It looks like Gaussian with a log link has an MAE of 4,109. Gaussian with a square root link has the MAE of 3,955, which is lowest. The only link functions that were appropriate were the identity, log, square root, inverse, squared, and inverse. The others were not used because this is a regression problem and not a classification problem. Okay, so this is just Gaussian. Let's also look at the other families. Let's look at gamma. So out of all of the gamma Gaussian models, the square root link provided the lowest error. And here are the gamma models. It looks like the lowest is the identity link. Out of the gamma models, the lowest was the identity link. Now, what others do we have? We also have the inverse Gaussian. And it gets an error when trying to use the inverse squared. I also tried the inverse Gaussian. The inverse square link did not converge. This is common if the model's not a good fit. Like if I tried to fit, let's say I said binomial, link equals logit. This would also create an error. Well, this is actually a different error. Say link equals log. That will also create an error. So if you get an error when trying to fit a distribution like this, it just means that the model is not appropriate or not a good fit. And this is also failing. Inverse Gaussian link equals inverse. It's giving me not a number value. Not a number. Well, what are you trying to do? I guess because you're trying to take an inverse of something. So the inverse is 1 over something. So if you try to divide by 0, it will give you a nan value, which is possibly what this is doing. The inverse link returned NA values as well. So here are the results from the 3 models that did work, and it looks like the inverse Gaussian with the identity link had the MAE of 4.1. So out of all of these, the lowest seems to be the Gaussian with the square root link and the gamma with the identity link. The 2 models with which had the lowest MAE on the test set were the Gaussian with the square root link and the gamma with the identity link. Okay. Task 6. Choose between 2 models based on the domain of the mean of the response distribution and the range of the link function. The following information will be helpful. what I've done is I've just chosen two possible models. Gaussian square root link, gamma identity link. This question is to choose between the two. This table shows the distribution family and the range, or the output, the possible output values. I should let me rephrase that. Uh, the range is the support. It's the so if you have a Gaussian distribution, a Gaussian random variable can be any real number. It can be any positive number or any negative number. A binomial distribution can only be 0 or 1. Gamma is always positive, right? Inverse Gaussian is always positive. And so how does this connect to our problem? Well, we're trying to predict claims, and claims are always positive. It's very, it's not possible to have a negative medical cost. I mean, you could have someone, you could have like a chargeback, for instance. Um, but in this data, there are no negative claims. So the target distribution is positive. And so only response families which are positive um, make sense. Otherwise, it would be possible for the model to make negative predictions. They might be very unlikely, but they are still possible, uh, even if these are unlikely. The gamma the gamma distribution is always positive, but the Gaussian allows for negative values. And we're also looking at the two link functions. So the first model was the Gaussian with the square root link. And the second model was the gamma with the identity link. So the gamma, so if you have a link function, it relates the linear predictor x beta to the mean of the distribution. So if you say that your distribution is Gaussian and your link is log, you're saying that the linear predictor is equal to um, the log of mu, where mu is the mean of the distribution. Now a Gaussian mean can be positive or negative, right? A gamma mean, because the gamma is only a positive, it's always positive, right? And so its average, its mean can only be positive. And so this means that the linear predictor should always be positive, right? Through the link function, the linear predictor of the gamma distribution, the mean of the gamma distribution should always be positive. The link function relates the mean of the response distribution to the linear predictor. In the case of the Gaussian family, the mean can be any positive or negative number. In the case of the gamma, the mean must be positive. So if we use an identity link, we can get negative numbers. See, because the inverse mu is equal to, if in the case of the identity link, the mean function is that mean is just equal to z. It's equal to the linear predictor. In the case of a log link, mu is equal to the exponent of z, and the exponent is always positive. So the range of the mean is any positive number. If you use the inverse link, the mean is equal to 1 over z, which can be positive or negative. If you use an inverse square, then the mean function is 1 over the square root, and the square root is always positive, and so the range of the mean is always positive. If you use a square root link, then mu is equal to z squared, and the square of a number is always positive. Now, technically the square root can be positive or negative, because technically the square root doesn't have one inverse. Technically, it could be, plus or minus the square root of z. But in this case, we're only considering the positive part. So all of this to say, in our two cases, we're looking at Gaussian with a square root, which is fine. The Gaussian and square root, the Gaussian model with square, let's be more explicit. Of our two models, the Gaussian, the GOM with the Gaussian response and square root link means that the mean of the Gaussian, the square root link is means that the mean of the Gaussian will be positive because the inverse, or because the mean function for the square root link has a positive range, right? I'm looking at this table right here. Let's just copy this table here into the report. This is shown in the bottom right cell of this table, right? The second, the gamma model with identity link has a problem. Do you see why? Because the gamma mean must always be positive, but the identity link technically allows for negative values, right? Because if you look here, identity link implies that the mean function is just mean is equal to z, which is just x beta. And so it could be the case that if you got some data that your model would fail. So not in this data. In this case, it converged. But it could be that you get another data set and the model doesn't work. So based on this information, I chose to use the Gaussian model with the square root link. So let's just make this more clear. So here Here's the Gaussian model with the square root link. Here is the gamma model with the identity link. Right? This actually has a lower MAE too. In addition, this has lower MAE on the test set. Okay, task 7. Examine the residual plots to determine if the model is a good fit. So here I need to change this to Gaussian square root, because that's the model that I wanted to use. And then here are the residual plots. And the residuals, if this was a perfect model, these residuals reverse fitted would be scattered all around 0, which is not true. You can see that there are these weird patterns. When you look at the normal QQ plot, if this was a perfect model, these would all be in a straight line. It looks like that's almost the case for lower values, but once you get up to higher values, there's a significant deviation. And the scale location plot, if this was a perfect model, would also be scattered around 0. However, you can see that there's a very clear trend. So um, the residuals plots provide diagnostics to tell us if the model is a good fit. Uh, if this was a perfect model, then the residuals first fitted left would have no pattern. The normal QQ plot center would have all points along the 45-degree line, and the scale location plot right would also be random. The residuals first fitted have a clear pattern. The QQ plot shows very good quantiles up to about 1, and then a sharp deviation right about here. See, this indicates that the model is a good fit for low cost claims, but a poor fit for high cost claims. Scale location plot shows that the residuals change, depending on the predicted value. And it might be good to provide a little bit more theoretical understanding, just to help the grader to understand. So you could say the assumptions of a GLM are that the deviance residuals are normally distributed, residuals are scattered around 0. Okay, the next task, fit a GBM using the given parameters. Your assistant has already run a grid search to find the optimal values of 4 hyperparameters. For each of these parameters, describe what it does and whether a higher value would increase or decrease the likelihood that the model overfits. Overfitting means that the model is too sensitive to random noise in the training data, or that the the performance on the training data is good, but the performance on the test data is poor. Okay, so in other words, if you had a linear model with like 1,000 predictors, that would be overfitting most of the time. Yeah, so here's the code. So it says your assistant has already run cross-validation to find the best type of parameters. So here you can see there's a tune grid, which basically creates multiple combinations of interaction depth, entries, shrinkage, and minops per node. And then there's a function to get the MAE. And then there's this train control method, which uses cross-validation repeated 3 times, and then it fits a GBM and caret for every combination of parameters. So I'm just going to run this. And the challenge of this question is really just an explanation. It's not a question of statistics, it's just about comprehension of statistics. So GBM is an ensemble method of decision trees where the where many an ensemble method that uses boosted decision trees. First, a single tree is fit, and then the residual calculated. Oh, let me rephrase that. First, the residual is. Oh, let's keep this at a higher level. GBM is an ensemble method that uses boosted decision trees. Each tree considers the residuals. Considers the residuals from all of the prior trees, and the model iteratively improves by adding more trees. GBMs are more flexible than GLMs because they this isn't asking. This is going off on a tangent. The question is just asking you to explain what the different parameters are. So the parameters are entries, interaction depth, shrinkage and n.minobs in node. Entries is the number of decision trees that will be used in the ensemble. More trees leads to a more complex model and increases the likelihood of overfitting. Interaction depth is the, let's find out. Let's go to our documentation and type in $GBM. And then we'll go down to the parameters. Integer specifying the maximum depth of a tree. An integer that specifies the maximum depth of a tree, right? So higher values lead to deeper trees, which means that more variables are used and overfitting becomes easier, right? Just imagine that you had a linear model. If you added in more predictors, it's easier to overfit. If you have a decision tree that's taller, then you have more splits, which means that you have more variables in the model. Shrinkage is so I'm just reading right here this definition where it says shrinkage. Shrinkage is the parameter applied to each tree in the expansion, also known as the learning rate. This is the rate at which each tree's contribution adds to the predicted value. So a higher shrinkage leads to the model's predictions getting updated faster, aka it's faster learning, which makes it easier to overfit. N.minobs in node is an integer buying the min number of observations in the terminal nodes. A lower value means that more granular trees, aka trees with more branches, are allowed, which increases the likelihood of overfitting. Yeah. Let's see. Okay. Task 9. Compare the GLM and GBM based on the MAE of the test set. Explain the advantages and disadvantages to using the GBM. Based on these findings, which model would you recommend for this problem? So we've run this section to create the GBM. And now we'll evaluate the MAE, and wow, we see that it's 2,561. What does that mean? It means that on average, the model is either above or below the median claims by about $2,500 per year. The best GLM was about $4,000 above or below the claims on average. So that is it's a significant difference. So the mean absolute error is the average amount by which the model is above or below the annual claims, medical claims. The MAE of the GLM was about 4,000, but the MAE for the GBM was about 2,500, which is better. Okay, and this also asks to compare advantages and disadvantages. So advantages, disadvantages. So the advantages to using the GBM is that it automatically detects outliers, fills in missing values, detects non-linearities, detects interaction effects, has higher predictive power. Some of the disadvantages are it's difficult to interpret, takes longer to train. So it's difficult to interpret, more difficult to interpret than a GLM. It takes longer to train, is more challenging to deploy than a GLM, which can be, written out. It can just be converted into a spreadsheet. Okay. Based on these findings, which model would you recommend? And I'll say one of the main disadvantages to the GBM in this case is that there are fewer statistical assumptions needed, whereas the GLM made assumptions about the distribution family and link, which were not met, as we can tell by looking at the residual plots. So based on these, I would choose to use the GBM for this problem. The GOM may work well for low-cost claims, right? Because when we looked at this QQ plot, you could see that these are approximately normal for low values, as the QQ plot was approximately normal for low values. We could truncate the claims at a certain value and use the GOM for these policies. So whenever they ask you to make a decision, it's always a good idea to consider other options. What are the pros and cons? What other solutions would be possible? What are some of the trade-offs? Rather than just giving a single answer. This is a way of increasing the likelihood that you will be saying what the grader wants to say, right? If you say more things, it's more likely that you will get closer to the right answer. Okay, task 10. Interpret the variable importance in partial dependence of age, BMI, and smoker status. Okay, so here's the variable importance. You can see smoker, yes, is most important, followed by BMI and age. And then these other variables are less important. You can see this kind of like a hockey stick. So the top three variables are explaining the vast amount of the claims. The top three variable, most predictive, smoker, were smoker, BMI, and age. And these explained most of the claims. Uh, the other variables were making or less predictive. And also the partial dependence. So first I should explain variable importance for GBMs is a way of measuring how much each variable contributes to the overall predictions based on the uh, on the on the on the on the information gain based on the importance of the variable across all of the decision trees that were used in the ensemble. Variables that are more important in trees are higher in the tree. Information gain and Gini score are both ways of measuring importance. In a GBM, the importance, yeah, I think that's good. And then I'll say the top three most predictive variables for smoker, BMI, and age. And then for the partial dependence, first we can see the So what the partial dependence plot does is it attempts to show the effect of a variable on the response when adjusting for all of the other variables in the model. So it looks at the training data and it fits models for each value of the variable that you're looking at for all other combinations of variables in the model. So if age is equal to 20, then it says, okay, um, let's consider models. Let's consider observations where age is equal to 20 and BMI is equal to 4, and BMI is equal to 5, and BMI is equal to 5 and smoker is equal to yes, and BMI is equal to 5 and smoker is equal to no, etc., etc. And it does that for uh, every combination that's in the training data for age is equal to 20. And it does the same for age is equal to 30 and for age is equal to 40. And so for each value of age, it then averages the model's predictions over all of the other combinations that are in the training data. And what it's trying to do is to approximate the effect of age on the response. But as you know, it's taking an average, right? And averages can be misleading. So here's the average of age against the claims. Here's the average of age against the claims for smokers versus non-smokers. You can see for smokers, this is much higher on average than for non-smokers. Likewise, this is the average for against BMI, against body mass index. So you expect that as BMI increases, claims would increase because people would become less healthy. When you look at it for people who are not smoking, however, there's basically no effect at all. So this is all. So this average here is all being explained by these smokers who are just being grouped together when you only look at the plot like this. That's a lot of words. I probably won't type all of this out. I'll just say the partial dependence is a way of showing the impact that a variable has on the prediction after adjusting for all other levels, all other variables. Uh, this is done by considering the average for age. This is, for example, for the variable age, uh, the model uh, looks at examples, at records, where age is equal to 20 and all of the other combinations of the other variables that are in the training data. Then it takes the average predicted value and this is the point on the graph where age is equal to 20 and y hat is equal to about 10,000. This is it then repeats this process for all other values of age. Um, because this is taking an average, smokers get grouped together with non-smokers. When I split by smoker status, I see that the impact of age on claim costs is more severe, steeper for smokers than non-smokers. For BMI, it looks at first like BMI increases medical costs directly. But when splitting by smoker status, I see that this is only being caused by the smokers. Okay, now I think that is it. Now the task is to write the executive summary. So I'm going to split the window and so that I can read everything that I've written, and I might zoom out a little bit. And they say your executive summary should reflect the information provided from task 1 to 10 as relevant to Freedom Health in non-technical language. So I'll start with the business problem. The business problem was Freedom Health is looking to accelerate their underwriting process by building a predictive model. So we can help Freedom Health to build a predictive model that will accelerate their medical underwriting process. This analysis compares two different modeling approaches and demonstrates and modeling approaches and their this analysis identifies this analysis compares two different modeling approaches for predicting future medical costs. Freedom can use these results, this model, to decide on which policies it wants to use this model to assign risk to policies. And then I'll say that we found that using a GBM results in much better using a GBM can result in much higher accuracy by a factor of 50%, because as the average error is about 2,000 annually, 2,500 of almost 50% as the average error is 200 rather than 4,000 with the current GLM approach, with the current method, which is the GLM. We found a new model approach that has much higher accuracy by a factor of almost 50%, as the average error is 2,500 annually rather than 4,000 annually. And then I'll just provide some interpretation. So the most predictive, the three variables, smoker status, body mass index, and age, are three factors which contributed most to a person's medical costs were smoker status, body mass index, and age. The other variables and we can also look at the sign. So costs increase as BMI increases, although this effect is different for smokers versus non-smokers. I realized I've included this graph twice. I meant to include age here. Let's go back and get this. The same is true for a person's age. Costs increase as age increases, but smokers are more expensive. Smokers have smokers have higher costs than non-smokers. Okay. And now I'll just go through each of the specific tasks. There's not really much else that I can do when it comes to interpretation. Yeah, so I would then go through each of these specific tasks. Oh, before doing that, let's just wrap up this little introduction and say freedom should consider smoker status. Freedom should freedom should have a way of telling if a policy holder is a smoker or not prior to making an underwriting decision, as this has a significant impact on their future costs. At age, yeah, this might be difficult info to get because people may not be honest. I'll say age is publicly available, and so this info, this data should be accessible. We began, now I'll go back and start narrating each of the tasks. We began with an exploratory analysis of the data. We looked at 1,338 policies from the prior year, and I had 6 different variables for each related to the person's, the policyholder's demographics, health status, I'll just say BMI, gender, age, and number of children. We found that the claims distribution was heavily skewed and that yeah, I don't need to narrate every single detail, just the important parts. Found that that those with a higher BMI tend to be more expensive on average than for smokers. For non-smokers, just I guess this graph right here, I found that yeah, we created additional features in order to improve the predictive power. We only began with 6 variables. And so we added another 3 based on our understanding of uh, of health costs, family size, and age categories. Uh, we then considered unsupervised clustering methods. I'll just say unsupervised learning in order to find patterns in the policies which we did not observe from looking at the graphs and summary stats. We used hierarchical clustering, which allows us to set the cutoff threshold to choose the number of groups that we cluster into. We did not find any clear patterns, and so this info was not used further. Finally, we considered some GLMs. So Freedom has been using GLMs for future uh, predicting future claims. And so we first wanted to replicate the type of model that Freedom would have used. A GLM is a common used modeling approach that relates the target variable to the values of several input variables simultaneously at once. This is commonly used in insurance rating because it is easy to interpret and can adjust for different claims distributions. We tested many different combinations, 4, 8, 12. We tested 12 different GLMs and evaluated and chose the best one based on a blind test on holdout data. We found that the best GLM had an average error MAE of how much was this? Remember, it was the Gaussian with the square root link. 3955 per year. found problems with this model. The claims distribution, the assumptions, the assumptions regarding the residuals were not met, indicating that the model is not a good fit. Specifically, the residuals, the deviance residuals, were not normal for large claim amounts, and there were clear patterns in the residuals versus fitted values. This implies that a GLM is not a good model for this problem if the goal is to, have, if the goal is predictive power. Right, and now we then we looked at a GBM. This is a powerful ensemble method which combines the results of hundreds of individual decision trees into a single model, and has a number when we tested this model on the same holdout data as the GLM had been tested on, the error was almost half, 2,500. Let's get the exact number, 2,561. This has the advantage of well, I don't need to list the advantages here. I'm going to keep this rather brief because this video is already rather long. You could keep expanding to this. You could keep talking about some of the advantages and disadvantages. You could talk about the bias variance trade-off, about model interpretability, about future considerations of compute power. How does Freedom Health want to use their model? Do they need it to abide by certain regulatory constraints? Are there limitations to using a GBM because it's not interpretable and you will not be able to explain it to insurance regulators? Things like this. After this, finally, it's a good idea to then just write a brief conclusion. Just makes the report look more professional. Say things like, this report showed how Freedom Health can improve their underwriting process, as well as detailing steps for building uh, a type of a model, a new model, a better model. Ways of improving, I'll say future research, future considerations would be to, one, get additional data, as we only had 6 predictor variables. Uh, if freedom can gather more information about its policy holders, then the performance of the models will be better. 2, we could um, we could also consider I'll just leave it at that. If you think of any other future considerations, it's always a good idea to include them. And that is the solution. Before I finalize this, I will go back and just look. I'll look over my. I'll look over the project statement just to make sure that I haven't missed anything. If you are in the real exam and you finish like this would be a great time to get a break, go out and get some juice or some type of energy, give your mind a 5-minute break, and then come back and review. That will really help you to catch anything before you finally submit the report. If you have left something out or made a serious mistake. So let's just go through the specific tasks. Task 1 was to write a high-level summary of the data, include the number of records and number of variables. So the data consists of 13,000 observations. Yeah, I'll say prior to this report, we already cleaned and we cleaned the data and removed missing values. Task 2, explore the target variable charges and its relationship to smoker and BMI. The distribution is, okay, we have some stuff here explaining that. We're looking at a lot of graphs. It would also be a good idea to include tables as well as graphs. Now these are all numeric, but you could show like the mean for smokers versus non-smokers. Like in this graph, let's say let's group by smoker, summarize mean is equal to mean charges, median is equal to median charges. Some people like to look at graphs. Other people like to look at tables. It's good to include both. Uh, okay. So yeah, so this is the mean is much higher for smokers. The mean is much higher, 32,000 for smokers than non-smokers. Eight, 4, 3, 4. This is the median. Okay. Where's my project statement? Explore the target variable, engineer additional features. This was worth 9 points. So I want to make sure that I've included a lot of detailed description here. So they already have what the description should be. So I'll just show them, I guess, my counts. I'll give them the counts of the values. And it doesn't have to be, the counts if you create new features. The point is just include evidence that you did the thing that they asked you to do. Oh, and this is actually redundant because I have the age bucket right there. So I don't need that. Okay. Hierarchical clustering. I think this is enough information. Fitting the GLMs. I think that I have a good description here. Yeah, I think I have enough information. I think this would be enough to pass. So if you had more time at this point, your best bet would be just to keep writing. Just keep putting text onto the word. Just keep putting words onto the page. And